Determine whether the following 3 points are collinear. To do this, we're going to use the first 2 points to write the formula for a line as a parametric curve with parameter t. Then we're going to see if the third point is given by that formula and any value of t at all, right? So this problem statement probably doesn't make a whole lot of sense, but these 3 coordinate triples are defining a point in 3-dimensional space, x, y, and z coordinates.
That problem is for section 11.2?
11.2, yeah. And this word collinear means they belong to the same line. And the deal is this, like any 2 points fully defines a line. And so if I give you over here this point in space and then over here this point in space, that fully defines a line in 3-dimensional space. You could imagine if I were holding a string like this one, 2 points fully define what that line is. And so if I give you 3 points, that third point may or may not lie on the same line. In fact, most points aren't lying on this line. There's only very, very few points relatively that are actually lying on the same line. So collinear means the third point is actually on the same line that's given by the first 2 points. And that's what we're trying to figure out. So what I'm trying to say is let's come up with a parametric curve. So the coordinate x is given by the parameter t, the coordinate y is given by the parameter t, and then the coordinate z is given by the parameter t. And I want this parametric curve formula to give me the first 2 points. I should be able to come up with a little curve that gives me both the first point and the second point here. And so just thinking about x, let me say that x of t is equal to, we'll just say t. Okay, so what that tells me is for the first point, t must be equal to 0, right? So that way x is equal to 0 for my first x coordinate. And then what this also tells me is that for the second point, t is equal to 1, because my second point, the x coordinate, is 1. And then we'll also say for the third point, t must be equal to 3, right? Because my x coordinate of my third point is 3. Okay. So then what I need for my y coordinate is so that when y is evaluated at 0, I get -2, because that's the y coordinate for the first point. And then whenever I take my y function and I evaluate that at 1, I need the y coordinate to be +1, because that's the y coordinate of my second point up there. I'm trying to define a line in space. So the other thing I know about this y function is that y of x, or sorry, I should say y of t, my bad. Here we go. Y of t is going to be something like mt plus b, right? I have a slope, and then I have my t parameter, and then I have some constant, right? So this is just the formula for a line. And now my job is to say -2 is equal to that slope times 0 plus b, and +1 has to be that slope times 1 plus b. Does it make sense how I went from here to here? Okay. So now I have a system of equations, but it's actually going to be pretty easy to solve this system of equations the way we set it up. Because if I start from this first equation here, I've got negative 2 equals m times 0 plus b. This tells me that b is equal to negative 2. And using that, I can rewrite the second equation so that it says 1 is equal to m times 1 plus b. So I could write 1 equals m minus 2. And that tells me that m is equal to 3. And now I can write that my y of t function, if it's a linear function and if it contains the 2 points, it has to be y of t equals 3t minus 2. Now we have to repeat the same thing with my z-coordinate. And here's what I know. Is my first z-coordinate was 3 and my second z-coordinate was 0. So that means whenever t is 0, that means z is 3. Whenever t is 1, that means z is 0, I think. Yeah. 3, 0, 3, 0. Perfect. Also, again, I need this z function to be linear. It needs to be a linear function of my parameter t. And so I'm going to write mt plus b. And now we just have the same sort of situation where I have to figure out what is my m slope and what is this b constant. Okay? So just like before, we're going to write a system of 2 equations. And it's going to look like 3 is equal to m times 0 plus b. And then 1 is equal to m times 1 plus b. This first equation is trying to tell me that b is 3. And then if I take that, I can rewrite my second equation as 1 equals m plus 3. And that's telling me that m is equal to negative 2. No, I think I messed this up. Here we go. Found my mistake. That 1 should really be a 0. Because my z-coordinate is equal to 0 whenever t is equal to 1. And so that means that 1 should be a 0. And so then this should be m equals negative 3. There we go. That's better. So if I combine these ideas, my z-coordinate is given by my parameter t with this linear function. Z of t is equal to negative 3t plus 3. Okay. So right here in purple and then right below it in blue, I really did the same procedure twice. Once for the y-coordinate and once for the z-coordinate. For the x-coordinate, I was a little bit lazy and I just decided that x of t was just going to be t. You actually have the freedom to choose what kind of linear function x's. Or alternatively, you could just choose an arbitrary linear function of t for y or for z, but you only have the freedom to choose one of those. That's what you call like choosing the parameter. And you could actually make this problem work with a bunch of different linear functions of t, but I just think that t is the simplest linear function of t, and so that's what I went ahead and went with. In any case, I now have a function that gives me my x-coordinate as a function of t, my y-coordinate as a function of t, and my z-coordinate as a function of t. And I know that whenever I plug in t is equal to 0, I will get my first point up here. And whenever I plug in t is equal to 1, I will get my second point. And whenever I plug in t is equal to 3, I will get the third point. Or at least I hope so. If I plug in t is equal to 3, I definitely get the right x-coordinate. The question is, if I plug in t is equal to 3, and I get the right x-coordinate, will this also give me the correct y and z coordinates? If it does give me the right y and z coordinates, that means these points must be collinear. And if it gives me different y and z coordinates, that means that third point doesn't lie on the line that I found between the first and the second point. I know this is kind of a long problem, there's a lot of steps here. But let's use my y function, and we're going to plug in t equals 3 for the third point, and I would get 3 times 3 minus 2, which is 9 minus 2, which is 7. So what I'm saying is, if these are collinear, then my third point has to have y-coordinate of 7. And my third point does have y-coordinate 7, so that's so far so good. The last thing is if these points are going to be collinear, then my z of 3 function has to give me a z-coordinate of -6. So again, let's take this z function, plug in t equals 3, and I have z of 3 is -3 times 3 plus 3. So that would be -9 plus 3, which is 6. And that is a z-coordinate of, -6. -6. And so that does give me the right z-coordinate. And so this verifies that what happens is, yes, these are collinear. Okay, really long problem. All right, so let me just rehash what we did. We said the first 2 points, those fully define a line that passes through three-dimensional space. Okay, so I know that I can parametrize a line and say, let me allow one parameter t to be like the real number line, take on all values, and then I will make x, y, and z functions of t, making them specifically be linear functions of t, so that I'm actually talking about a line in three-dimensional space. And then we're going to see after that if we can make the third point fit along that equation, or fit with my parametric equations, or my parametric functions as a function of t. And if it works, then it works, and the third point is lying on that line. It's collinear. And anyways, I'll post this recording on Canvas, and you can go back and rewatch this if you want to see the whole reasoning and how we did this again. There's actually a shorter method of doing the same problem, and so we're going to show you that as well, a little shortcut method. And we're going to start with this definition. We're going to say that u and v, my two vectors u and v, are parallel if u is equal to some scalar times v, right? So I'll write kv, But k is just like any number, right? That's just a scalar. That is the definition of what it means for vectors to be parallel. And so, a quick example. If I said u is equal to 1, negative 1, and v is equal to 42, negative 42, I would say that yes, these two vectors are parallel to each other. And if I were looking at this formula, what is k? 42, yeah. Because u is just equal to 42, sorry, it would be 1 over 42, huh? It would just be 1 over 42 times v. Okay. So, let me give you another example really quick. What if I had the vector 1, 3, and over here I had 81. What goes in this blank for my first entry to make these two, yeah, it would have to be 27 in order to make these two vectors parallel. If it were anything other than 27, it wouldn't be parallel. Okay. Then, let's have this problem. Determine whether the following 3 points are collinear. So the same problem as we had before. But this time, to do this, what we're going to do is define a vector u using the first 2 points, and another vector v using the last 2 points. And then we're going to check whether these vectors are parallel. And it turns out that if u and v are parallel, then these points are collinear. Okay, so the way I'm going to make my u vector is I'm going to take the difference between the first 2 points, and so I might write something like 1, 1, 0 minus 0, negative 2, 3. So my u vector is going to have entries 1 minus 0 is 1, 1 minus negative 2 is 3, and then 0 minus 3 is negative 3. Okay. So my v vector, I'm going to find it the same way, just using the second 2 points, the last 2 points. And so I would write 3, 7, negative 6 minus 1, 1, 0. And 3 minus 1 is 2. 7 minus 1 is 6. And negative 6 minus 0 is negative 6. Okay. So like I said, if u and v are parallel, then these 3 points are collinear. And if u and v aren't parallel, then these points are not collinear. So is my blue vector here, 1, 3, negative 3, is that parallel to 2, 6, negative 6? Yeah. And the parallel equation is saying that u is equal to k times v. Then what would k be? 1/2, yeah. Yeah, you're right. I mean, if you went the other way, you swapped the vectors, it'd be 2. Yeah, no worries. So, anyways, the answer is yes. Those vectors are parallel, so that means those 3 points are collinear. And this is a lot shorter, right? I mean, answering the same question, but this method was a lot faster. Stephen?
Does it matter what operation you use to combine the vectors? I mean, the points, the 3 points. Like, could you add them instead of subtracting them? Or would that not work?
You have to subtract them, but the order in which you use to subtract them doesn't matter. And also, if you wanted to use the first 2 points for u, and then for v, if you wanted to use the first and the third point, that would work just fine. Or if you wanted to use the last 2 points for u, and then for v you want to use the first and the third point, that would be fine. And like I said, the order of subtraction doesn't matter. But you do have to subtract. You can't add them.
Okay.
Yeah. Yeah. If you swapped the order of subtraction, you used 0, negative 2, 3, minus 1, 1, 0, it would just make all of these values negative. Well, it would make the 3 a positive. But it would be negative 1, negative 3, plus 3. And that would just mean that our k value is negative 1/2. But the value of the k doesn't actually matter. It just matters that the k exists, right? And it meets that formula. So these would still be parallel and would still work to give us the right answer. Okay. Here we go. Suppose the 3 points below are the vertices of a triangle. Determine whether the triangle is a right triangle, an isosceles triangle, both or neither, right? So you could have a right triangle that's not isosceles, like you might have like a 3, 4, 5 right triangle. You can have an isosceles triangle that's not a right triangle, right? So you could have like a triangle that's like 20, 23. That would be isosceles, but definitely not a right triangle. There are some right triangles that are isosceles, right? So we could have this triangle, right? And so that's both a right triangle and isosceles. Or you could have a triangle that's none of the above, right? So like the 1, 2, 3 triangle would not be right or isosceles. Okay, so we've got these 4 categories, and we're saying these 3 points that we're given, these represent the vertices of a triangle living somewhere in space. The question is asking, are these going to be forming a right triangle, an isosceles triangle? Is the triangle they form both? Or is it neither? So, I'm going to start off solving this problem by finding the lengths of the edges. Okay? Now, the way I'm going to find the lengths of the edges is I'm going to say that my vector u is going to define the difference between the first 2 points. My vector v is going to talk about the distance between the last 2 points. And then I'm going to come up with another vector that I'm going to call w, and it's going to be the difference between the first point and the third point, right? So, in other words, u is going to be 0, 6, 1 minus 3, 4, 0. So it would be negative 3, 2, 1. V is going to be 3, 5, 5 minus 0, 6, 1. And that is going to be 3, negative 1, 4. And then lastly, W is going to be 3, 4, 0 minus 3, 5, 5. And so that one is 0, negative 1, negative 5. Okay. So my points that are given to me, the first, second, and third point, are again the vertices of a triangle in space. Now my vectors u, v, and w are telling me about the differences in the coordinates between the first and the second vector. Sorry, what I meant to say is the first and the second point, the second and the third point, and then the third and the first point. Now what I'm going to do is if I can find the norms of these vectors, that's going to tell me the length of the side that connects the two vertices. So the norm of u is going to be square root of 3 squared plus 2 squared plus 1 squared. So that norm, or this side length, is going to be square root of 9 plus 4 plus 1 is 14. Okay. Now the norm of v is going to be the square root of 9 plus 1 plus 16. So 26, I think. And then the norm of w is going to be the square root of 0 squared plus 1 squared plus 5 squared, which is going to be the square root of 26. Okay. Now, the norms of these vectors are the side lengths, the length of the sides that connect the points, my vertices of my triangle. So what do you notice? Yeah, it's isosceles. So isosceles means two of the lengths are the same. And I can tell that the lengths of those last two sides are the same. They're both square root of 26. So I know it's either isosceles or maybe it's isosceles and a right triangle. The way that we would check to see if this is a right triangle is by using the Pythagorean theorem, right? So if this were a right triangle, it would have to satisfy a squared plus b squared equals c squared, right? Where c squared is my hypotenuse. Now you guys probably realize this, but the hypotenuse has to be the largest or longest side of your triangle, right? Hypotenuse is always the longest side. So in this case, we'll say that, square root of 26 is my longest side, so that means, c squared would be 26. That means b squared would be 26, and then a squared would be 14. And this Pythagorean theorem equation is not true, right? And so since this does not meet the Pythagorean theorem, this is clearly isosceles, but not a right triangle. Okay. Man, this is a lot of material. I'm starting to get worried. And the thing is, I did set aside Monday for a review day, but if we had to, we could also finish up 11.3 on Monday. Ideally, we would make it through on a normal week, but we'll see. Here we go. Determine the center and radius of the sphere given by the following equation. This is what we call the equation for a sphere in general form. The general form equation is always expanded, like it's fully expanded as a polynomial. And you collect all the terms on one side of the equation so that the other side is 0. Usually the right-hand side, we set it equal to 0. However, if you're looking at the general form of the equation, it doesn't tell you what the center and the radius are. If you want the center and the radius, we have to sort of rearrange this a little bit to put it into the standard form equation of a sphere. So I'll show you how to do that. We're going to have to write all of the x terms together. And then all the y terms. And then all the z terms. Okay. And then I'll set this equal to negative 19. I'll just move that 19 over to the right-hand side, okay? And so what I have left in the blank is a place to add just a little constant value. And this is called completing the square. And in completing the square, what we're saying is we have a quadratic polynomial that looks like x squared plus bx plus c, and we're going to fill in that c constant by taking b divided by 2 and then squaring it. Okay? That's how we're going to fill in the blanks. And if we fill in the blanks like that, that's going to make each one of these a perfect square. And then I'll show you what happens next. What happens after that is we're going to write x plus b over 2 squared, because that would give us x squared plus bx plus b over 2 squared. Okay. So then what goes in this blank is going to be 9 divided by 2 squared, right? It would be 9 over 2 squared, or you could write 81 over 4. And then what goes in this blank is negative 1 squared, or just 1. And what goes in this blank would be 5 squared, which would be 25. But if I want to add those on the left-hand side of the equation, I also have to add them to the right-hand side of the equation to keep my whole equation balanced. And so in my next step down here, I'm going to write this as x plus 9 halves squared plus y minus 1 squared plus z plus 5 squared is equal to negative 19 plus 81 fourths plus 1 plus 25. Now, the center of my sphere is given like this. My x-coordinate is going to be negative 9 halves. My y-coordinate is going to be positive 1. My z-coordinate is going to be negative 5. And so that is the coordinates that give me the center point of my sphere. And then my radius is going to be the square root of all of this junk. So it would be the square root of negative 19 plus 1 plus 25, which is 7 plus 81 over 4. So that would be 109 over 4, I think. Okay. You can check my math later, but what you end up doing is on the right-hand side of this equation, that should be the radius squared. That actually should be the radius squared on the right-hand side. And so once you add the fractions, you'll want to take the square root to tell you what the radius of the sphere is. Okay. Sorry for moving so quickly. I just really want to make sure that we finish 11.3 at least by the end of the day, Monday. And so I've got one more example in 11.2, and then we'll move on. It says, choose the correct values for y and z, which are over here. I want to choose the correct values in order to make the following 3 points collinear. And so we're going to use the same strategy that we did the shorter way, is we're going to make a u vector and a v vector based on the first 2 points and then the last 2 points. So I've got this. For my v vector. 3 minus 1 is 2, and then I have y minus 1 and z for my v vector. For my u vector, I'm going to have 1, 1, 0, minus 0, negative 2, 3, and that is 1, 3, negative 3. Okay. I said this earlier, but if u equals kv, then these are collinear points. In other words, if that u vector is parallel to the v vector, then we know that those 3 points are collinear. So what I want to do then is take this equation, and u is just 1, 3, negative 3. And v is 2, y minus 1, z. So my first question for you guys, what is k? What does k have to be? Well, it has to be 1/2, yeah. Because if I'm looking at the first entry, 1 is 2 times 1/2. So that means k has to be 1/2, for sure. And if k is 1/2, then 3 is equal to 1/2 times y minus 1. And negative 3 has to be equal to 1/2 times z. Now let me multiply both sides by 2. I get 6 is equal to y minus 1. So that means y is equal to 7. And then over here, negative 6 is equal to z. Okay, so if I want these 3 points to be collinear, then this last coordinate, this last set of coordinates, this last point has to be 3, 7, negative 6.